So I'm going to talk about geometric distance regular graphs today. And I'm afraid it will not be so long as yesterday. It will be about 30-40 minutes. I'm sorry. Let's get started. In this part, we're going to show that most Grassmann graphs are characterized by their intersection. We have no idea whether a representation proof like for the Johnson graphs is possible, but it looks like that is quite unlikely because of the twisted Grassmann graphs do exist. Most of the results I'm going to represent are due to Metsch, building on the work by Bose, Neumaier, and others. If a distant regular graph is physique k as small as equal theta min, then a maximal clique, and that means a complete subgraph in gamma has order at most 1 minus k over theta min, the smallest eigenvalue. I will give, this is called the Diazo Bound, and I will give proof later today. So, and we call a clique of this order a Diazo clique. It has very nice combinatorial properties, more than the order. We say that the distant regular graph gamma is called geometric if the edges of gamma can be partitioned in Diazo cliques. There are many examples of geometric distance regular graphs, the Hemming graphs, the Johnson graphs, the Grassmann graphs, and so on. But for example, the twisted Grassmann graphs are not geometric. And that probably is a real problem, but how to overcome that, we don't. That geometric distance regular graphs have a small integral smallest eigenvalue because the order must be an integer. So if 1 minus k over theta min is an integer, then theta min must be irrational. But theta min is an algebraic integer, and if it's irrational, it must be an integer. And in this section, we're given sufficient condition for this regular graph to be geometric. So Chris Costello observed that the Diazo bound for strong irregular graphs also holds for distance regular graphs. So the following lemma is called the Diazo bound. We take a distance regular graph with intersection array blah blah blah, and with distinct eigenvalue k, theta 1, and so on. Be a clique with order c. Then c is at most 1 minus k over theta. Theta d minus theta d is the same as the smallest eigenvalue. How do you prove this? It's not so difficult. So you take the standard sequence for theta d, you take the standard representation for theta d, and let Vc be the vertex set for c, and let Q be the c times c, symmetric c times c matrix indexed by Vc, by the vertex of the clique, such that the xy entry is just the inner product of sigma x with sigma y. And that's for x and y in the. It's fairly easy to see that you have ones on the diagonal and the rest u1. So that means that the Q is 1 minus u1 times identity plus u1 times the O1 matrix. J is the O1. Q is positive semi-definite because it's a Gram matrix. Its row sum must be at least 0, yes? Although there's only non-negative eigenvalues, yes? This means that C minus 1 times U1 plus 1 must be greater equal to 0 with equality if and only if the sum over all the vertices of C, sigma x, must be the 0 factor. U1 is theta over k, we obtain the Diazo. And you can use this, this sum is 0. You can show that if C is a Diazo clique, then there exists a constant alpha, so that any vertex C outside either alpha or 0 neighbors. And partially linear space is a tuple X is P, L, and I, where P is a finite set called the point set, L is a finite set called the line set, and I is an incidence relation between P and L. So that any two distinct lie on at most one line. That means there is at most one line incident to both. And usually the incidence relation is clear, and then we omit it. If not clear, then we write it. And you can define the point graph of X as the graph with vertex at the points, such that any collinear points are adjacent. That means any 2 points that are on a line, if they are on a line, they are adjacent. And if they are not on a common line, then they are not adjacent. In a similar manner, you can define the line graph. Note that a geometric distance radius graph is the point graph of a partial linear space with at lines Diazo cliques. So if you have a geometric distance radius graphs, then you see that every edge is covered exactly once by the Diazo clique. That means that any 2 of those Diazo cliques cannot intersect in more than 1 point. So that gives you the partial linear space. Twisted Grassmann graphs are the point graph of partial linear space, but they are not geometric. Not every vertex lies on that. So now we start with results of Klaus Metsch. He showed the following results. This is an extension of the clique method developed by Bose and others. Some people call the Bose-Lasker method, and you have many names for this. And it is not so complicated. It looks very complicated here. So let's see an amply regular graph with parameters phi, k, a, c. That means it has phi vertices. The valency is k. Any 2 vertices, phi vertices have a common neighbors. And if I take 2 vertices at distance 2, they have c common neighbors. Now we assume there exists a positive integer s such that the following 2 conditions are satisfied. +1 times a plus 1 minus k to be bigger than c minus 1 times s plus 1 choose 2. And second condition is a plus 1 is bigger than c minus 1 times 2s minus 1. Then we can define a line as a maximum clique with at least this a plus 2 minus c minus 1 times s minus 1 third. The phi, then the x is phi c L, where L is the set of lines as defined above, is a partial linear space, and C is the point graph of X. We have another thing is that every vertex is in most S lines. So we have many things. So I will prove this theorem. It's fairly easy to prove it. So the proof is fairly easy. So we assume there exists an S plus 1 claw, say with vertex x, y1, y2 up to ys plus 1, where x is associated to all the yi. So x is the middle vertex. So the sum of vertices associated to x having at least 2 common neighbors of the yi common neighbors is at least is the number. Why is this true? Because every vertex is adjacent to, you have s plus 1 times a1 plus 1 vertices that are adjacent to y1 to ys plus 1, including the vertices y1 to ys plus 1. Yes, we also consider that the vertices y1 to ys plus 1. We have at most k vertices, yes, in the local graph. So that must mean that those vertices have at least 2 neighbors, because there cannot be anything else. Now we have exactly s plus 1 choose 2 pairs yi, yj, with I is not equal to j. Pair yi, yj have exactly c common neighbors, including x, yes. S plus 1 times a plus 1 minus k should be at most s plus 1 choose 2 c minus 1. And this contradicts the first condition. So therefore there exists no n plus 1 clause in gamma. So this was the first condition. For the second condition, we need to show that any 2 lines intersect in at most 1 vertex. or 1 point if you prefer that. C1 and C2 be two different lines intersecting at least two vertices, say X and Y. Then the intersection is at most C, as otherwise they are not different lines, yes? Because they have a vertex that is in C1 that's not on C2, and a vertex in C2 that is not in C1, because both are maximal cliques. And on the other hand, X and Y have exactly A common neighbors, yes? So now we look at the number of common neighbors of X and Y in the union of the C1 and C2. Number is at least 2 times A plus 2 minus C minus 1 times S minus 1. The order of the every C1 and C2 have both at least order this. And we subtract C from it. We want to remove the intersection. And then we add C minus 2, because that is the maximal. It cannot be less than this number. This is 2A minus 2S minus 1 times C minus 1 plus 1. See that A plus 1 is, then we use the condition that A plus 1 is bigger than C minus 1 times 2S minus 1. So we see that this number must be more than A, and this finishes the proof. Yes? So that means that is in contradiction. They have more than A common neighbors, so that's not possible. So that gives you a contradiction, that finished. So in 1995, Klaus Metsch showed the following theorem. The Grassmann graphs J, Q, and D are characterized by the intersection ray if n is at least a maximum of 2D plus 2 and 2D plus 6 minus Q. This gives, if Q is small, then you have to have a little bit larger underbound for n, and if so Q is 2 and 3, this gives you need a little bit larger lower bound. You also need the diameters at least 3, because for diameter 2 there are many. And we will give a sketch of the proof below. So what happens for n is 2D and n is 2D plus 1? Because except for Q small, we believe that that should be also the case, that they are characterized by the intersection ring, but the method by Klaus Metsch did not work for those particular cases. That's Q is 2 and Q is 3. But that should be not too difficult to repair, I hope, but we don't know on this moment. Gavrilyuk told me that he has some progress on this. In 2005, with Edwin van Dam, we found the twisted Grassmann graph have the same parameters as the Grassmann graph, J, Q, 2D plus 1D. So the Grassmann graphs are not determined by their intersection. The J, Q, 2D plus 1D, and you can, we have at least one more example, because the twisted Grassmann graphs are not geometric, so therefore they cannot be isomorphic to the Grassmann graph. Another reason is the twisted Grassmann graphs have the vertex, they are not vertex positive, so they can never be isomorphic to them. So with Gavrilyuk, we showed that the Grassmann graphs J, Q, 2D are uniquely determined if D is at least 9. For Q last, we can lower that D to D at least 6, but I didn't want to put the precise statement. It's not that important whether D is at least 9 or a little bit different. I don't think that is that important. So now we will look at the proof of Klaus Metsch. So we assume that we have this distance vector with same intersection array as the Grassmann graph J, Q, and D, where n is at least the maximum 2D plus 2 and 2D plus 6 minus Q, and D is at least 3. So then it follows by the previous result that gamma is a point graph of a partial linear space, so that each point lies in a most qd minus 1 over q minus 1. As the smallest eigenvalue of gamma is equal to this number, minus qd minus 1 over q minus 1. And k is this number, k times qd minus 1 times q minus 1 times qn minus d minus 1 over q minus 1. So that gives that any clique, and hence any line, has at most q times qn minus d minus 1 over q minus 1 points. So every point lies on qd minus 1, q minus 1 lines, and every line must be in that factory. Trivial, yes? So this shows that gamma must be a geometric district graph. And note that any vertex outside the line has either q plus 1 or 0. You can calculate the alpha in this case, and that is q plus 1 in this case. And for those who are familiar with the classical parameters, the alpha of the is exactly this q, or q plus 1. I forgot what it exactly is, but it's very close to q plus 1. It's either q or q plus 1. And we need to use a result by Ray, Choudhury, and Sprague of 1976. They characterize the partial linear space coming from a Grassmann graph. So the theorem is as follows, and you can look at the Brouwer and Neumaier theorem 9.3.3 for the statement. So you want that the number of, so you have a partial linear space. So it says for some integer q, we don't assume it is in prime power. The following conditions are satisfied. Each line has at least q squared plus q plus 1 points. This is where we need the diameters at least 3. Then we get this for 3. And each point is on more than q plus 1 lines, and that is also necessary because if we have diameter at least 3, that is also true. And we have the condition if we have a point P and a line L that have distance 1. So that means that P is not on L, but P has neighbors in L. Then there are exactly q plus 1 lines through P meeting L. And assume that 2 points P and P prime are at distance 2 in the point graph. Then there are precisely q plus 1 lines L through P that are distance 1 with P prime. And the last condition is somehow a desperate condition that we don't want, that it is not. We want that the circular graph is connected, the point graph. The point graph of X is a Grassmann graph, and you can make it slightly more precise if you want, but you can say, let's not do that. And hence, Q must be in prime power. So we did not assume Q is a prime power, but you get that Q must be in prime power. You must have a fit of order Q. That's the reason you have to have a prime power. So I already said that because of diameter at least 3, we have that every line has at least q squared plus q plus 1 vertices, points, and any point lies on at least q plus 1 lines, more than q plus 1 lines. Maybe it's not so clear on this moment, but after I say what I mean to say, then you see it is immediately. We already have seen that any vertex outside the line has either q plus 1 or 0 neighbors on the line. So this says that conditions 3 and 4 are satisfied as C2 is q plus 1 squared. So that means there are always, and now we have the last condition, yes? So because C2 is q squared, q plus 1 squared, and every point, if I take 2 vertices distance 2, then there are q plus 1 lines that are closer distance, that distance 1 to this first vertex. And because q plus 1 squared is q plus 1 times q plus 1. Yes? So that is the reason why everything is satisfied. And so we get the Cosmographs, and so we are done. Yes, that is how the proof of Metsch works. So he used this work of Ray, Chowdhury, and Sparks from 1970. And what you can show is that the third and fourth condition imply that the C2 graph, that is the subgraph induced on common neighbors of two vertices, that this two is a Q plus 1 times Q plus 1 grid. And Hans Kuipers in his PhD thesis, I think it was in the early 1990s or late 1980s, showed that the first condition can weaken that to that every line has at least 3 Q points, but that doesn't help with the diameter bound. You need still diameter. And I already said that if the diameter is 2, then there are many strong radical graphs. Strong radical graphs is essentially the same as the distance radical of diameter 2. The same parameters as the Cosmographs there, because you can make certain kind of designs and they always exist there in. So now I will give one more remark before I end my talk today. I'm sorry, it is a little bit short. Klaus Metsch used a similar characterization of binary forms graphs, but of course he needed to use a different result than the Ray, Chowdhury, and Sprague result. What he showed is the following, and it is less satisfying for binary forms graphs, because you have still many open cases, and we don't know what to do there. So for Q is 2, then we need that E is at least D plus 4, and for Q at least 3, we need that E is at least D plus 3. What happens with D plus 2 and D plus 1 and D, we don't know. This is something nobody knows, and I'm sorry for that. So that is very open. For Q is 2 and E is D, Gavrilyuk and I showed that they are characterized by its intersection array, but that was just a lucky case. So we were very lucky that we could do that case. For Q is 3, it doesn't work. Like there are too many possibilities still. So we don't know what to do for Q is 3, for example. Okay, that is where I stop for today. Thank you for your attention. Yeah, Paula, I'm finished.
Right. So you said that in your result with Gavrilyuk, you said JQ, I think it was 2DD. Oh, thanks. Yeah, you said that JQ 2DD is uniquely determined by its intersection arrays if D is greater than or equal to 9, right?
Yes, I will. Yeah. That will be the rest of the week. I will talk about that part.
Oh, okay. So I should say my question till then.
So then, that I will. That is for the rest of this week. I will try to give the proof for that. At least give some ideas for the proof, because that proof is much harder than the proof for Metsch results.
Yeah, I guess I can save the questions for later times when you actually talk about, you know, that JQ 2DD case. But yeah,
that
thanks.
I will.
You want to ask my question for? So Jack, I wonder, how do you know the Q is a prime power? Did you construct the PG? Did you construct the projective geometry?
You have a. So you mean why is Q a prime power? Because you have to construct an projective space. Yes, I guess that is what it is. You take you have an as underlying space and vector space over a finite field.
Go ahead and bite that for me. Thank you.
In the Grassmann graphs, are there any known forbidden configurations, specified distances that are known to not exist for any Grassmann graph?
Not that I know of. I'm not aware of that sort of thing, but maybe Sasha Gavrilyuk knows more than I do in that respect. But I'm not aware of it, let's say so.
Any other questions? Okay, let's thank Jack again.
Okay, thank you. See you tomorrow then.